In this video we're going to discuss the idea of an exact sequence of abelian groups. So suppose we've got some abelian groups A, B and C and some homomorphisms alpha and beta. Okay, so then we recall the image of alpha, so that's the set of B and B, which B can be written as alpha of A, some A and A, and the kernel of beta, so that's the set of B and B for which beta of B is 0. Okay, so and it's standard that both of these are subgroups called B. And let's note, we could consider the homomorphism beta composed with alpha from A to C, and that might or might not be the zero homomorphism. So let's ask, beta composed with alpha is 0. That means that for all A, beta of alpha of A is 0. But to say that beta of alpha of A is 0, that means that alpha of A lies in the kernel of beta. Okay, that's just what we mean by the kernel. The kernel is the stuff that gets sent to 0, so that's what it says. And that's but the things of the form alpha A, they're just the image of alpha. So this is just the same as saying that the image of alpha is a subgroup of the kernel of beta. And so the definition we want to make is that this sequence star is said to be exact if the image of alpha is equal to the kernel of beta. Okay, so half of, to say the image is equal to the kernel, that sort of says that the image is contained in the kernel and also the kernel is contained in the image. So the first half of that the image is contained in the kernel, is equivalent to beta composed with alpha being 0, as we just explained above. But then you also have to have that the image of alpha contains the kernel beta, and that's kind of not automatic. So this condition is like half of exactness, and then the other half is something else. Okay, so that's what we mean by an exact sequence. Also, say star is short exact. If it's exact, and also we have the property that alpha is injective and beta is surjective. We can rephrase that if we want. Okay, so firstly, alpha has to be injective, which is the same as saying, by a very standard fact, that the kernel of alpha has to be 0. And then the image of alpha, right, so we're saying it's got to be an exact sequence, which means the image of alpha is the same as the kernel beta, like say there. And then beta is supposed to be surjective, so to say that beta is surjective is the same as saying that the image of beta is C. Okay, so short exact means kernel of alpha is 0, kernel of beta is the image of alpha, the image of beta is C. Okay, so some basic examples. So firstly, there's one kind of short exact sequence that we can do for arbitrary abelian groups. We can define, say, I from A to A plus B sending a to a comma 0, and we can define p from a plus b to b by p of a pair ab is just b. Then what's the kernel of p? Okay, that's the set of pairs ab for which p of ab is 0. Let's write it in. So that's the set of pairs ab for which b is 0, which is just the set of pairs a comma 0, a, and that's just the image of I. So the sequence that's certainly exact in the middle. The image of the kernel of P is the same as the image of I. It's also clear that I is injective and P is surjective. So this is a short exact sequence. Okay, so sequence which occurs like this, that's called a split short exact sequence. Okay. But yeah, here's another one which isn't split. Okay, okay, so let's fix a positive integer n. So I'm going to define okay, so instantly I'm going to you see I've decorated some of these arrows. I've got to put a tail on this arrow and a double head on this arrow. That's kind of a fairly standard convention for put a tail on the arrow indicates it's injective, and put a double head indicates it's surjective. So here Ix is just going to be nx, and px is going to be x plus nz. Okay, so so this I multiplication by n, so that's certainly injective because n here was a strictly positive integer, so it's not 0. So multiplication by n is injective. If nx equals ny, then x equals y, and then every element of z mod n is a coset like x plus nz for some x. So this p is surjective, and then we find that the kernel of p, that's a set of x such that x plus nz is nz, and so that's just equal to nz, and that's the image of I. So the sequence is short exact, but z is not isomorphic. So z plus z mod n, right? I mean, this group on the right certainly has some elements of order n, whereas the element in the integers, everything has either every non-zero integer has infinite order. So see, we don't have any elements of order n on the left-hand side. So these groups are certainly not isomorphic. So it's not a split sequence, right? It's not of the same type as we mentioned in example 1. Another interesting class of examples. Okay, so let n m be positive integers. Okay, we're going to again define homomorphisms like this. I of x plus nz is going to be mx plus nmz. Okay, so we need to check that this really is a well-defined homomorphism. We had a lemma about that in the last video. I mean, the point is, if I replace, they've got the same coset, I could represent it also as x prime plus nz, some different x prime, but then x and x prime would be congruent mod n. So when we multiply them by m, they would still be congruent mod n times m. So we get the same coset on the right hand side. So this is a well-defined map, and p of y plus n m z is just going to be y plus mz. Again, that's also well defined by, it's even easier in that case. Okay, so what's the kernel of I? So that's the set of x plus nz such that mx plus nmz is equal to the zero coset nmz. So that's the set of x plus nz such that mx is divisible by nm, which is the set of x such that x is divisible by n. Set of x plus nz such that x is divisible by n, which is just consists only of the zero coset. Because if x is divisible by n, then x plus nz is just the same as the zero coset. So this is the trivial group, therefore I is injective. And it's more or less clear that P is surjective. Okay, and then P of y plus nmz is 0 if and only if y plus mz is the zero coset, if and only if y is nx, is mx for some m, in which case y plus nmz is the same as I of x plus nz. And so we see from this that the image of I is the kernel of P. So this is a short exact sequence, and you can ask, well, is it split or not? So using the Chinese remainder theorem, the sequence is split if and only if n and m are coprime. Prove it carefully would require a few extra steps, but the Chinese remainder theorem is certainly the central point here. Okay. So there's some examples about exact sequences. And one more example I wanted to give. Let's define alpha from z squared to z squared by alpha of xy is y0. Then the kernel of alpha, that's a set of pairs xy for which y0 is 0, 0. That's a set of pairs xy, y is 0. So that's the set of pairs x0 for which x is in z. But that's kind of obviously the same as the image of this alpha. Okay, because alpha of xy is y0, so everything of the form something comma 0 is in the image. Okay, so So we do this. Now we see we've got an exact sequence like this. Yeah, and so we could just kind of keep chaining these together. So we could do an infinite sequence like this. So the image of each map is the kernel of the next. And that this is what we mean by saying that the whole sequence is exact. Okay. So that's a good collection of examples of exact sequences. Then we should kind of explain a little bit what this theory is for. One point, so a key point is that many sort of natural statements that you might want to make can be expressed in terms of the exactness of certain sequences. First one, let's say okay, so suppose we've got a pair of homomorphisms like this, where the first homomorphism is 0. Okay, I mean, to say that the sequence is exact, that means that the kernel of beta should be the image of this 0 homomorphism, and the image of the 0 homomorphism is a 0 group, and to say that the kernel of beta is 0 is the same as saying that beta is injective. So in particular, okay, so this happens where this is valid whenever the map coming in here is the 0 map. Yeah, so it could happen that the group A is the 0 group, right? In which case, if A is the 0 group, then this homomorphism here is just forced to be the 0 homomorphism. There isn't anything else it could be. Okay, so this guy is this is exact if and only if beta is injective, and there's a kind of counterpart for that in terms of surjective things. So this is exact if and only if the image of alpha is the kernel of this 0 homomorphism. But the kernel of 0 homomorphism is the stuff that gets sent to 0. That's going to be all of B because the homomorphism is trivial. And to say that the image of alpha is B, that's the same as saying that alpha is surjective. So in particular, it could happen that the group C is the trivial group. If C is the trivial group, then this homomorphism from beta 0 is forced to be the 0 homomorphism, and so this first observation here applies, and we see in this case that surjectivity, exactness is equivalent to alpha being surjective. Okay, so and another thing we can say is if we've got so what happens if we've got both homomorphisms being 0? Well, that's equivalent to saying that the the image of this homomorphism here is okay. Now the image of this zero homomorphism is 0, and the kernel of this zero homomorphism is B. Okay, so sequence like this, where both homomorphisms are 0, the only way that can be exact is if the group in the middle is the trivial group. So in particular, if you had an exact sequence like this, with both groups there being 0, then that's the only way that can be exact is if B is the trivial group. And then yeah. And then what about a sequence like this? So remember, if we've got a sequence that's not just a 3-term sequence, but a longer one, when we say it's exact, we mean that the image of each map is the same as the kernel of the next one. This is saying that the kernel of beta is the image of zero homomorphism, which is 0, and the image of beta is the kernel of C going by 0 to D, which is C. But for kernel of beta to be 0 is the same as beta is injective. And for the image of beta to be C, that's the same as saying that beta is surjective. So what we conclude is that the sequence like this is exact if and only if beta is actually an isomorphism. So in particular, if you've got a 4-term sequence and the first and the last groups are 0, then the whole sequence to be exact, that's equivalent to beta being an isomorphism. And then just a final thing. Okay, so suppose we've got a sequence like this, and we tack a 0 on both ends, right? So say this sequence here is exact. What does it mean? It means that the kernel of this map here, kernel of alpha is the image of 0, which is 0. So alpha has to be injective. Then the image of alpha has to be the same as the kernel of beta, and then the image of beta has to be the kernel of C to 0, which is C. So beta has to be surjective. So so this is. And that was exactly what we meant by saying that this is short exact, that it's exact at B, the image of alpha is the kernel of beta, but also alpha is injective and beta is surjective. Okay. So we'll just have one more example about exactness here. So defines alpha from Z mod 4 to Z mod 4 by alpha of I plus 4Z is 2I plus 4Z. In Z mod 4 is basically 0, 1, 2, 3, and and we're doing this doubling map, so 1 goes to 2, 2 goes to 4, but 4 is 0 mod 4, and then 3 goes to 6, but 6 is 6 is just 2 mod 4. So we find that the kernel of alpha consists of 0 and 2. Those are the only things that get sent to 0. So that's the same as the image of alpha. And so we see that we can do this thing again where we just do this alpha repeated endlessly. And that's again an exact sequence. So the last thing we want to say about exact sequences is this little lemma here. Okay, so it's suppose A alpha to B and then my beta to C is short exact. Then A is isomorphic to alpha of A, or in other words, the image of alpha. And then beta induces an isomorphism from B mod alpha of A to C. Okay, so here, you know, alpha of A, that's a subgroup of B, so we can form the quotient group B mod alpha A, and the claim is that's isomorphic to C. So it follows from this B is finite if and only if A and B are both finite, and if so, then the size of B is equal to the size of A times the size of C. Okay, so firstly, we'll, you know, so alpha is injective. That's part of the definition of what it means to say it's short exact, and it also and if I just regard it as being a homomorphism from A to alpha A, then it's surjective in that context, because alpha gives us an isomorphism from A to alpha A. Now beta is surjective by assumption, and therefore the first isomorphism theorem says beta induces an iso from B mod the kernel of beta to C. Okay, that's just what the first isomorphism theorem tells us. But the kernel of beta by assumption is equal to the image of alpha, and so we see that B mod alpha A is isomorphic to C. And thirdly, yeah, so we now each sort of divide B into cosets of alpha A, right? So size of each coset, of course, is just the same as the size of the group you're thinking about. So the size of each coset is equal to the size of alpha of A, which is the same as the size of A, and the number of cosets is the size of the group of cosets, which is this quotient group here, which is the size of C. So the total size of B is size of C times size of A. So here I sort of wrote this as though these things are all finite, but if size of A is infinite, then each coset has infinite size, and each coset's a subset of B, so B has infinite size. And similarly, if there's infinitely many cosets, well, each coset has at least one element, so B would then have to be of infinite size. So that basically proves that. Okay. So that's everything we need to say about exact sequences for the time being.